week 11, we got some other systems, and basically we have, let's see how many types. Transverse floor. It's transverse floor. I'm going to show you the details, and I will wait for you to tell me what you think. Is it a precast or is it in situ? So we're going to go through them by one by one, but let's check how many types we have. The first type you're going to be, we will be talking about is the trans floor. That's one we will go through, and another one it's ultra floor, which is which can take higher capacity. So the two types now, trans floors and ultra floors, they are slabs, they are floors. And the last element we will be talking about is AFS, which is kind of well implemented and highly used in the construction industry, architectural framing system. It is for structural walls. It's kind of help to have different type, like very quite durable product. And we will see about the advantages and all construction challenges. So basically, yeah, we will go. That's the third time. I want to double check if there is. I think that's basically what we have to go through. So three types of other construction systems we just want to conclude your topics with. The first one was the trans floor. Second one, ultra floor, and the third one is ASF walling systems. Having a look to the first one, basically what's happening here. Now, let me just focus with you on this picture. Can someone tell me what he or she think about this system? Is it a precast or in situ system?
Precast.
Okay, any other responses? I'm just trying here to put questions for you, so it's going to be similar to what you can see in the final exam. So one student suggested it, or he responded to be, he responded in terms of the construction type of this floor system, and it's a precast. Any other ideas there?
Yes, precast.
You think as well precast, no problems. Now, the answer is it is combined, precast and in situ. Now, I told you it's combined. It means that there is part of the slab that will be placed on site that will significantly help you to avoid a lot of propping and formwork need on site. Then later on, you're going to be pouring the upper part, the other part, or basically it's the upper part of the slab. Can someone tell me which system was kind of similar to this we studied before? So the answer is basically it's combined. It is partially precast and partially in situ. Now, as I'm going to explain further, like this part we're seeing so far, it is precast. It's done in the factory. And like this whole piece, see this whole piece I'm framing around, it is built in the factory, and they're going to come crane it in its final position. And then once the formwork, there's kind of void. I will show you the details later because it's not fully concrete. It's like a hollow section. Then they're going to be pouring above the precasted section, and that's in situ. So because we're going to be pouring on site, it's going to be also the part we're pouring later, it's in situ. So that's why it's combined. Now, can someone tell me which system we had before over the past weeks, which is kind of similar thing to what we're talking about here? Any thoughts? Excellent. Yes, hollow core. Hollow core was kind of same thing, but hollow core was the reinforcement was fully inside the hollow core units, which going to come from the factory. And then we had just the top screed. It was about 100 mil or 80 mil screed on top of the hollow core slabs. And as I said to you, that board we screed on top, it's also structural because it's got a mesh. It's got some steel we put. So hollow core right was a combined flooring system in terms of construction on site and on site and precast. Now, one of the key advantages is you don't need propping, you don't need any formwork below, because so you have ready to construct and ready to construct floors below the slab. So as soon as you put the precast part on top, other tradies can actually go under and start doing whatever they have to do, services, whatever other construction need requirements. So that's the key advantage. It's fast, it saves time, and it can go up to specific spans. So that's the first system. It's, yeah, as it says here at the very start, is combined precast and system concrete, fast to erect, act as permanent formwork. That's the key points. So you just, again, when you read this, you need to know that system, you need to know the key advantages from it, and try to compare it with other systems we've been talking about. And I'm sure you know about hollow core as well. Saves time and money. This is kind of talking about the same thing. If you save time, it's fast to erect. There is flexibility in construction things, but the design engineer will kind of, like as you can see here, it can be the precast section can be formed to the shapes required. It does not always need to be rectangular shapes. So if you remember the hollow cores, they will come in strips, like what you did in assignment 2, and what I've seen some groups doing. Well done. And when you put the hollow cores, they're gonna come in about the 1.2 meter, 1.5 meter strips. If you had a void inside your building, you have to put supporting beams around the void. Now with this transfloor, the voids can be kind of allowed for in the factory. You don't need to worry about it. So it's kind of got flexibility in construction. Yes, we can construct irregular shapes easily because you can see here we've got this semi-triangular shape, semi-rectangular shape. Yes, as I said, services holes can be formed during manufacturing. It's unlike precast, the hollow cores, where when you construct them, you have to frame up the trimmer beams. People don't know what I'm talking about. Assume this is a floor beam, a floor plan for a building. And let's say we've got our hollow cores running. Let me just change the color here. These are the hollow cores, which are every 1.2 meters. They're running along the shore direction, similar to what I expect you to do in assessment number 2. Then let's say here we've got a void. We need to have a stair void, like here. So what we have to do here, we have to design and build during construction trimmer beams. So this will need to be stronger elements, right? And another trimmer beam here. So we need the trimmer beams to actually allow for the void. Now, floor system, no, they can't do this in the factory. It's going to be inbuilt inside the slab. So that's a key difference between hollow cores and floor. Just going back to where is my, yeah, here we go, just hit it here. Yeah, for the soft will be really smooth. So as we know that the soft, the lower side of the slab, yeah, from underneath of the slab, it's typically really smooth. And hollow core will be quite rough. So that's something the architect need to allow for. And also as construction, you got to know if it's hollow core, it means that we're going to need to put plastering at the ceiling level for the floor below to hide such things. But the trans floors, it's going to be smooth. It's kind of ready for service. It may just need to be painted and all good. In terms of its construction elements, now you can see this kind of the truss system, right? The triangular lattice truss system. It is the key reinforcement element inside it. So you can see this triangular lattice truss system. It's already embedded and placed into the trans floors while it's built in the factory, and it will come like this to the side. So the key reinforcement element for those systems, they are truss systems. The triangular girder truss systems, they are built and the size of the bars, and these are the diagonals within the triangular truss system. They will be typically sized by the engineers, whether N16 bars or 20 or 12. They will be pre-placed in the factory within the precast section, which was also shown to you by these. You can see them here. So you can see these are the truss girders. They are partially constructed inside this 200 millimeter thick, or more or less, depends on the design, right? So the first elements we have here, we've got the reinforcement. There is also other secondary reinforcements running this way to cope with shrinkage and the small spans. So the way these slabs really works, the slabs will be the main girders that will be supporting the span are these kind of strips where the trusses are formed to be part of the strip. Then in between, the slab will be running in between the two strips, which means there are still reinforcement within the slab, as we're going to see in the next details as well. All right. So these bottom bars of the truss, so there are, as you can see, there's one bar at the top and two bottom bars. They're going to be acting as a bottom steel for the slab, for the transfloor slab. Right, so this shows you just advantages of trusses. They are number one, they're going to be used permanently to take the bending action and whatever tensile stresses the slab can experience. Number two, they are used to crane up the transfloors. You can see here, they are craning up the transfloor, and they can be in the small sizes, or they can be as large as you can see here. Just depends on the crane capacity you can have on site, or any other logistics the construction engineer can think about. If there is any questions we have here. No, so yes, handling. The trusses can be used for handling and transports, and they, as part of its design, they're going to be taking the bending action. So when you actually lift the transfloor panels, so that means this is the purple color is your concrete slab, and that's the steel, the truss. So you remember there is also a bar submerged inside the concrete already, like this. So as you lift up or crane up the transfloor slabs, the truss will be taking away the load from the concrete. So the truss got a temporary function, which is to carry the precast slab. So the actions will be kind of different. While you carry the transfloors, the truss will be under kind of negative bending action, which will be transferred to forces inside the trusses. And then the permanent positioning of the transfloors will end up imposing positive bending. So if you kind of lift this truss, the bending moment diagram will look something like this, but things will be different when you actually gonna be placing the truss floors in its permanent location. Now, this is someone will have a look here, they will say, but we do have propping lines. You can see there are propping lines here. That's correct. That's something similar to the bonding. Yeah, so we remember the bonding sheets. They can be without props, with one line of prop, with two lines of props. Same thing with transform floors. Sometimes they can go the full span, so you need zero propping. Sometimes they're gonna need few lines. It's the engineers who design those trans floors, or there are span tables, which the construction engineers can use. Span tables will tell you same kind of tables, almost similar to the tables you've used for last week for the composite slabs. They will have similar tables ready to use for the trans floors. So the construction engineers can decide on the spans if they need props or they don't need absolutely any number of props. All right, so basically from the slides, we can understand that the triangular trusses we have in the system, they're gonna act as a framing component to support and crane the precast sections of the truss floors. And then once it's in the final position, they're gonna be working with the slab to resist the permanent loads. Now, this is not the final. You're going to see next what we do after you place. Now, after they place the trans floors, sometimes you see those white parts, they are foams. They are polystyrene foams. They're going to create voids within the final slab. And think in the next slides, here we go, the green shaded area. It is a void. That's where you see, this part is where you see the white polystyrene foam. It is kind of there to just create a void. And definitely, what was the reason? Can someone suggest why you think we're putting the polystyrene foam more? What's the main purpose for that, you would say? Why do we have polystyrene foam more?
Acting as a suspension.
Say that again. Suspension. So why you can see the cross section of the trans floor, it's what we're seeing here. So this is the full thickness of the slab. Right? This is the full thickness, the full final thickness. Now, what the precasted section, it's basically what I'm gonna be, hopefully, it's basically gonna be this lower part. So let me clarify this. The 2.5 meters, it is the width of one trans floor panel. So you remember what was the case for the metal sheet decking in the composite slab last week? How wide was the section to put in one go? You remember that number, that width? What was the width for the
590 mm.
Say that again.
590 mm.
590. Yes, so about 600 millimeter width.
Yeah.
Yes. Today, the width of the trans floor, it can be up to 2.5 meters. Now, the red color, it is the precast section, which will come to us in the factory. And on top of it, we're going to have this triangular lattice submerged. And as I said to you, within the precast section, there is a mesh. The mesh is required. A mesh of steel, you can see the steel is running in this direction. And also you've got the steel running out of the page. So it's like a mesh, which I showed you several times ago. And you can see the lattice the trusses are also partially submerged. And also when this is going to come to Ukraine, it's going to come with the polystyrene. My question here was, why do you think they're going to be placing polystyrene, these white elements here? Whether you can see in this image or you can see them here as well. This. So basically the section we were looking at, we were seeing it from this side. So again, my question is, why do they use this white polystyrene elements? Excellent, yeah, Alia, that's right. To reduce the weight of the slab and the steel quantity. So basically, it is the weight. We're creating voids. It's something similar to the hollow core. Hollow core, they got the circular, kind of circular voids. Why are we doing this? We're doing it to reduce the dead weight. The dead weight usually the heaviest component in the structure. The density of concrete is 25 kilonewton per meter cube. So 25 kilonewton, multiply it simply by, say you have 200 thick solid slab, multiply it by 0.2. So in meters, this is going to give us 5 kPa. 5 kPa is actually 500 kilograms per meter square. That's just coming from a dead weight. Now imagine that usually the residential loads on a slab is only 1.5 kPa or 150 kilograms per meter square. And you can see the slab, 200 thick slab, which can span only 5 meters or 4.5 meters. It's by its own, it's 500 kilograms. So that's why engineers and construction ideas, they always come up with systems that will allow you to go for larger spans. You see your hollow core for your assignment went up to 14 or 12 meters or even more. If you want to use a solid concrete, you're going to have 300 thick, but remember, there is a lot of dead weight there. So yeah, you can see there's always polystyrene suggested in different ways that will basically help you to create voids, and voids eventually is going to reduce the dead weight of your slab. Right, so let's go back to our section and take it further. So that's the section I was talking about here. Right, so the colored parts, which is the red part here, as well as the void, they will, as well as the trusses, which are submerged or embedded into your precast section, they will be craned on site. And then later on, when everything is positioned, the top bars will be placed. So this is another mesh, which is to do with the top bar. Yeah, this is another mesh to do with the top bar. Then you're gonna hear we lapping the mesh. We have to lap it. There is in the engineering drawings, tell you how much lap we need to have between two sections. And then you will be pouring this whole slab all together. Right? Now, how thick is the slab? It varies depends on the span. It's like hollow core. Hollow core, you can start with about 250 thick hollow core slab, and it can end with 400 thick concrete slab. Depends on the span and the load it wanted to take. Same thing. I go through the same thing. So there are some details it's good to know about. You see the trusses will also serve as chairs to support the mesh. So usually these lattice bars or the triangular truss bars, they can also support the chairs or support as chairs for the top reinforcement. Yeah. So the length and the size of the truss floor, it's also a function of transportation. Generally, 12-meter trucks can be ordered reasonably with adequate economic measures, but if you want to go longer, cost will be high. This is the standard width, as I said to you. The standard width of the truss floor is 2.5 meters, and it is limited by normal transport restriction. Otherwise, you can go with widened vehicle, so you need more arrangement. You know, sometimes when you drive, you see two cars moving alongside a truck because it's wider than this figure. So it depends on where you're building it. Yeah, and we talked about the polystyrene voids or formwork, which typically it can take away 30% of the dead weight. So imagine if this was 400 thick slab overall, you did not allow for the polystyrene, you're going to be adding 30% of the 30% of the dead load will be increased if you did not allow for a polystyrene to be there. And nobody will do that. This is just another section from the suppliers. Yeah, so it is. So basically what you need to know from these notes is you need to know the system, you need to know all these kind of features. Yeah, these are the questions we like to ask you, the features. They are all what I've discussed with you. Yeah, the components. I think all of you will know the components. You've got the precast section with its own reinforcement. You've got the trusses, the triangular girder trusses. You've got the polystyrene. Then you've got the in situ component, which is poured on top of the precast section. So try as you study these things, always think about the components of the system, think about the considerations you need to, one of the considerations here, it is you need to know whether you need a single propping line, no propping line, multiple propping line. It's something, these three systems we're covering today, again, read them alongside the other systems we talked about, like, for example, composite systems, and also the post station and the pre-stress systems. We had a couple of pre-stress systems. They kind of talking about the same features and the same ideas. Right. So my point is, when you start reading for this topic, try to read it alongside the other topics. Don't read them separate. Okay, there is, this is again from the supplier, from one of the suppliers who manufacture and erect and construct. Nobody knows, maybe one of you going to be not managing the construction of entire building. You will be working for a manufacturer for one of those elements. Nobody knows what you're going to be doing. So they show you how you can connect this transport system. So the transport system I'm talking to you about this week is here. They show to you they can be forming a slab. So see here, they are forming a slab, which we've seen. And here as well, it is forming a band beam. So you can use this system to actually build a band beam and to build a slab. But the band beam here, we are cutting across the band beam. And here we are cutting on the longitudinal direction of the band beam, right? And there are some basic reinforcement detailing, like they're going to be some special bars lapped between the transfloor slab and the other supporting elements. Okay. So same technique, these can be built together. You can see here, this is a picture just showing you the band beam preparation, and this side is the slab, right? So it depends. I can see that the band beam here is just a solid band beam, because there is this is just a formwork. So this is just the band beam without the transfloor, and the transfloor will be supported on the band beam. But the band beams as well, if possible, they can be done as by using the transfloor path as per this image here. You can see with this image, or the suggestion by the manufacturer, they can say this band beam, if you want, you can build it with the transfloor system. This side here just shows you an edge beam, which is the concrete edge beam. So they can build it. They can pour, all the concrete can be poured in one go. Just need to prepare for all the reinforcement. And here you're going to have the formwork, the boxing out. You're gonna have a boxing out for the beam, and everything gonna be propped adequately. Yeah, and then so what I'm shading to you is how you prepare the formwork for a concrete beam. Then this formwork will be solid enough to support your truss floor. Remember that the truss floor will have its own propping lines as required. Same thing for the band beam. It's either can be formed as solid band beam, or you may think about deciding in using the truss floor if it's adequate to do such job. And then you may need a propping line. Then you can pour the concrete all together on top of the precast section, and also it's going to be poured for the beam as well. So this one, can someone tell me what they expect, what they're seeing here, the connection between which structural element? This is what we all know, that this is just the transfloor slabs. Can someone tell me what they're allowing for here? Yeah, any idea? What was this part? You know what 6 means, 7 means here? Yeah, that's it. Yeah, that's it. This is just allowing for the column. That's just creating a void for a column, which is basically supporting. There is a beam here. You can see there is a room. That's where they're going to be pouring concrete, as they call the upper part of the slab, the in-situ section of the transfloor system. They're going to be filling as well the beam, and obviously the column part will be poured as well. And it looks to me that this is actually the final floor level, because you can see the bars are cocked, they're not continued upwards. Right. So let's talk to that. This may be again a picture you see in a final exam and tell you, can you please annotate the structural components that you are seeing in this image? That's basically part of a question you may see. So can someone tell me what's this I'm going over? What's this?
Band beam.
This is a band beam. That's right, and it is basically an in situ band beam, right? And we studied this, and I expect students to know it. What was this system here? So in general, this is basically, remember, as we always do with you, we're going to be really specific in the questions. We tell you list, for example, 5 components. So band beam is number 1. Now someone can come here and say, what's this I'm highlighting here? It's the transfloor system we talked about today. That's the transfloor system, which is supported on the band beam. That's another component. Then you can talk about the elements of, you can talk about the elements of your transfloor system. This is a polystyrene formwork with the voids. This is the polystyrene elements. Yeah. And what's this here? What was this part?
The truss.
The truss. The
Lattice.
triangular lattice truss. That's right. Okay. Now, whatever we covered for you, we will expect you to answer. There are things I will talk to you about, but we don't. We won't, maybe if this element was not something we studied, we focused on during our week, you won't be, I won't be waiting for the students to answer. For example, someone is they may ask me, what's this? Can someone suggest what's actually this? It is something you studied, but you did not directly study. It was for something else. But anyway, I don't expect students in a final exam, all of them to answer this, so there will be no, that's why if there are effectively 6 elements in this image, I would expect students to answer 4. But if students answered it, that will be clear for them. So I just want to see how students' knowledge is at. Anyone knows what they think? What's this actually? Yes, yeah, plates. Yeah, they are the in-cast plates. You remember what we studied in the precast panels? We have the in-cast plates with U-bars in the back. That's same. But here they wanted it, maybe they're gonna weld, this may be the last floor, and they wanted to weld the column on top for a canopy or whatever. You know, like what you see in a car parks or something. So maybe they're gonna be having a column. After they pour everything, they're gonna have a piece of column and then they're gonna weld it on this plate. So this is simply, it's a precast panel, something similar to what we used, and what you're gonna need to work, what you're gonna need to show me this week. Again, I think people will need some support with their last question, the precast panels. I will talk about next week how you're gonna be examined about it. And there are some groups, they showed me what they're doing, but they didn't show me enough about the last question. So really, I expect you, and during the workshop, to try to finish answering everything and talk with me over this, whether during the workshop or to the end of the week, because I found students just kind of very few groups, they kind of, until now, they did not respond to that question. So this is basically just a cast plate they wanted here, but this is again was for required for this specific drawing. These are just reinforcement within the band beams, and these are here just the ligatures, shear ligatures that we need to resist shear. So this side of the slab is already poured, just to show you how things are. This side of the slab, it's already poured, like the in situ section is poured as well. And as we always say, they need to connect this slab with this side, so they have to keep some bars left outside. So they have to keep some bars sticking out from this slab. So when they're gonna come and place the bars up over the band beam, they should lap with these bars. And that lap depends on the engineering drawings. The lap need to be maybe 600 mils, 800 mils, depends on the size of the bar. Are there any questions you would like to ask me about these images? So basically here what we're seeing, it is just a formwork, which I showed you. This should be very solid formwork, because this formwork really needs to be solid enough, because it's going to be carrying the edge of the transfloor slabs. It's going to carry the edge. Remember, the transfloor slabs got 2 lines here of supports, and they're going to be supporting the transform lines slabs. Any questions you would like me to, or any detail you see? If you're going to be asked about something, you will be asked from images similar to this, and we just want you to tell us, yes, I know this system. That's the credit we want you to have from the subject. So that's one type of the slab, transform slab. We're done with it. Ultra flow. ultra floor. It is basically something which consists of things we studied before. So this is another flooring system locally used. Now, if you may end up in a company which really don't use this types, but however, if your company going to be involved in renovating an existing building or adjusting it, most of the buildings you see in the city are built with this system. So I can tell you, maybe with the current technologies of having post stationing available, accessible, got a lot of contractors to do it fastly for you. Maybe, again, I'm saying here maybe because this is still used if you want to avoid formwork, like the ultra slabs or the transfer slabs. They are still in business if you really want to reduce the formwork requirements, or if you sometimes got small spans and you want zero. You got a lot of cases where you want to build on top of existing developments, and those existing developments, they are in business, like maybe retailer shops. You cannot ask them to leave the premises. They want to keep their business running. So in this case, you have to think about flooring systems that require zero props, and that's where these solutions or these technologies can come in the discussions. So my point was, if you're gonna work in the area there, and you're mostly gonna be working with in situ concrete, the usual ones we talked about before the previous weeks, then that's normal. Remember, a lot of existing buildings, they were built based on these systems, and that's where you need to know about them still, because if you want to adjust things, you want to remove them, you want to make an opening, you want to place a column, you have to know what systems they have there. So it's still, you may end up searching for such system and know how it works. So yeah, basically ultra floor, it can, it's another system, which is, again, as we said, pre-stressed beams with in situ concrete. So it's kind of also combined construction type. And it's ribbed slab system. It's because of they got these kind of elements, and that's what I said. If you're gonna start making renovation works on existing buildings, like what they did about 8 years ago for the central station in the CBD next to RMIT University, they had a lot of upgrades there, and the existing floor was all the ribbed floor, the ribbed floor system. So to work with such systems, you have to know how they are framed to adjust them. So back to the system, as we said, part of it, this composite, this is precast. This precast element is actually pre-stressed. So that's why I'm saying it can take much more spans and longer, and most likely you need zero propping systems here, because they imagine you have precast, pre-stressed. They are pre-stressed, so they have good high capacity, higher than the transfloor slabs, right? So it is a ribbed floor system, ribbed because you're always going to see these kind of ribs from the soffit side or from below the slab. And these kind of ribbed beams, they are pre-stressed, right? And we all know what pre-stressed is. We talked about this a few weeks ago. Then they're going to be special sheets. They can be lightweight if the ribs, you can see the ribs are very close to each other. There's only about 0.5 meter. Those pre-stressed ribs, they're very close to each other. So in between them, they can be used very lightweight, not steel. It can be really lightweight plyboard, or any product that can temporarily sustain as permanently prop the concrete, but we're not using it as part of the structural system. So it's just to support the wet concrete until it's get hard. The other advantage of these sheets, which can be, it's actually more useful to have it cementitious or plaster-based material because it can help you with the fire rating and fire resistance, right? It's one of the key advantages or thoughts. You need something to fire rate the slab. So if you use metal sheets got less fire resistance. But the metal sheets, they got capacity to go for longer spans. If you want this to be a meter or 1.2, as we're going to see next, you will end up having a metal sheet, something similar to what we talked about in the composite slabs last week. You see the key advantages for the slab here to be really thin. So it is about 100 mil thick slab. And the overall depth with the ribbing of the pre-stressed precast beams, going to be 180 thick, right? There are different sizes by the suppliers, different thicknesses. It depends on the load. If you want to carry an office building, it's different than it. Shopping centers is different than residential. Right, so beam centers, we're talking the beams here, we're talking about the ribs. The beam centers range from 4.8, which is the case here, can go up to 1.5 meter, as I said to you. And once we go to such long spans, we will end up using heavy duty sheets, and it can be metal or steel. So the beams, the pre-stressed beams are quite strong, 65 MPa concrete with 9.5 low relaxation steel strands. So this is special steel strands, not the smaller than the 12.7 we used, as if you remember, with your, which also you have documented and working on in your second assignment. You're all going to need to show me those nice or adequately drafted floor plans for your precast slabs and floors in assessment 2. I would expect most of you have already used the 12.7 strands. This one got smaller strands. It is the 9.5 diameter, but it's only needed for those special type of rib beams. Yep, as I said to you, they come in a different types from the supplier. You've got the R beams, M beams, and C beams. Definitely this goes with more strands, more heavier to take loads, and the sizes are given to us. Right? You do not need to memorize those. I just want you to know the system in total, how it works. So I don't expect students to really. You won't get to be given a picture like this in an exam. If I want to ask you something similar to this picture, sorry, this is sketch or that sketch or this picture. That's how the question is going to come to you. I won't give you 2 lines saying to you, explain or describe this type of slab to me. You're going to be given an image or a picture, and you just need to annotate or know all the details, right? Maybe if we need to ask you, we're going to ask you, tell us what's the key differences between ultra floor and trans floor. So that's where you may not need a picture. You can work it out with correctly studying the topic. Right, so here, this slide will let you understand the different components, different types. We do have 2 infill options. As I said to you before, we either use, for those spacings. So for the clear spans between ribs, as we said, we've got the lightweight formwork, which is fiber cement reinforced infill. So this one, this is kind of got more advantage than this because it can help straight away with the fire rating. We don't need to spray it. The second option is something similar to what we talked just a few days ago, last week. Last week we talked about composite. We've gone slowly through the composite slabs, and what we use there is metal deck infill. Metal deck infill it is. something like a formwork nowadays. I know in different countries they may have different brands, but locally here there is the form deck, and the analyzer and all those other products I've shared with you, and I've given you those reading materials, and I showed you how to decide on the spans, how to decide on the negative and positive reinforcement. So you should be expert with that type of metal that we used last week, right? But again, if you needed to fire rate this floor for whatever reasons, maybe there was a car park here, and you've got residential floors here, so you need to allow for fire rating, so this may need to be sprayed. So can I think all of you, again, you're going to be forced kind of to use the metal deck if the spans were really long. You cannot use always the cementitious based formwork, permanent formwork, because it's got limited capacity, up to 600 spacing. And yeah, nowadays every few years you've got more products that challenges others, but it is up to whatever available. So some pictures about how people are doing it. You can see whatever the sketches and theories we're talking about, they are kind of reflected here. So the ribbed beams, they look something like what you can see here. They have already positioned it over some other supporting steel beams. I can see here they got steel beams to support the ribs. And then later on, now the ribs are ready to take the sheets. And it looks to me here the spacing is not significant. So they are ready to take the cement-based sheets. Then they can place the mesh, the steel, and then get your concrete poured. A lot of 40, 30 years old buildings in the city, they are built with such systems. And if modifications are required, definitely you need to know what systems we are using there. Yep, you can see here, this is just the formwork. So that's with fiber cement. In fact, they look something, these gray products, they are ready to take the concrete. You just need to place the reinforcement on top. And the cementitious based sheets, they will be taking the concrete weight. And that's it. The concrete should be ready. You can see here, this is the main concrete beam, which is, this is again, if you are on top of the subject, this is something similar to the pile caps we've seen in the retention systems. So the pile cap was partially built to allow for placing the floor on top of it, like what you're going to be thinking about for your second assessment. Same thing here. The concrete beams needs to be partially built with keeping the surfaces very rough and keeping the shear ligatures. These are the ligatures that takes shear partially extended. So when you're going to come and pour your in situ part of the ultra floor, it's all going to be poured together and everything will be engaged together. And your system is done, is built. Right? So again, how are you going to be questions? What knowledge you need to build from these topics is make sure you read the notes. It's not really heavy. Read the notes carefully, understand the pictures. If there's something not making sense, that's where you can come to me and we discuss that. If the spacing between your ribs get really long, more than 1.2 or even typically 1 meter, more than 1 meter span, and if there are no cement-based sheets to take such loads, you know the suppliers for these sheets, they will give you their maximum capacity. They will have their own tables. They will tell you if your span is 700 millimeter and the maximum concrete thickness above it is 150 thick, you can use this product. If you go higher, you can't. So, you know, same thing, similar to what you have experienced in doing for the composite slabs last week. The metal deck infill, you're going to be using something similar to, again, this is maybe have used in the very, very past where they got their different profiling for their metal sheets, but nowadays most of what you see is the formwork I shared with you last week, which is coming from one of the main suppliers, Lyset company. They got very well used metal sheets. Yeah, if you go within 1 meter plus spacing, you can place your metal sheets and then place your mesh or the reinforcement, which is mostly for shrinkage control as well. Then you're going to pour your concrete slab. You will be pouring your concrete slab, and that's all about it. But as I said, fire rating here will be missed. It was required. Other arrangements have to be done, whether it needs to be sprayed. Like students in Bendigo, they have the building, the engineering building they study in. It was kind of a new building, and it was built as a composite slabs, and most or kind of all the metal decks from below were actually sprayed, and it was painted then with black color to look nice. Okay, so yes, as I said to you, the suppliers for such systems will have their own tables, very friendly tables to use, which is this table I can see is more talking about the section properties, which is to do with the engineers, because they need to find capacity. So basically, construction engineers usually don't size up the sections. So these going to be nominated by you. Well, how it works sometimes, if you are the builder to decide on changing floors, then what you can do, the engineer will supply you with these values, with the loads. So they will tell you what the slabs can carry or the ribs, and then you just need to compare with this document. So the engineer will tell you what's the ultimate moment capacity. If they told you it's 15, then you can actually use the 150C because it's 22, but subject to checking the other capacities. You have to check. Usually the ultimate moment capacity will be higher than the crack control moment. Now the shear, yeah, you have to take it from the engineer. If the engineer said it can resist only the action from the load is going to be 16 or 17, then yes, the 150C is still winning, still okay. So that's what you do. Sometimes the engineers will supply you with loads, or sometimes they're just going to design it for you. Right, and then you can determine what size of ribs to use. All right, it's quite significant here. You can say 250C, you can take it's a lot of kilonewtons, 16, 8, 17, it's quite high. It's already 250. Okay, so that was your second type. And so I think, as I said to you, when you study these types, always in your review book, always try to look at the composite slabs we talked about last week and the hollow cores. So just to build that good understanding, comprehensive knowledge about all the systems we visited over the past 11 weeks, including this one. So, and you don't get confused to get ready for the final exam. So make sure you put solid days to now at the stage as preparation for after you finish your assessment by the end of this week, try to put some days for this subject to make sure you understand the topics very well. And if you have questions, ask. And then before the exam, put solid days to compare the systems together. So you don't get, because I do see students mix between the systems. Maybe you are asked about hollow core, they talk about ultraflow. They ask about ultraflow, they talk about hollow core. So you don't have significantly too many types, but they are similar. Make sure you understand them, and they should be enough to give you that knowledge you need to have when you practice in this in the construction area. So far we went through, or we have finished 2 flooring systems. And now we have the last kind of topic we want to cover. It is the a walling system. Okay, we are back to our topic. Have anyone before been using this system by any chance, or seeing it? Any students now, can someone brief us or talk to us about how they expect, how you would expect a concrete wall to be built? Like if I want to build a 3 meters high concrete in situ wall, maybe that was the case. There was kind of one method to go with it in the past, maybe 30 years ago, how they want to build a concrete wall. Say this is a concrete wall here. Where is my pen? It's hiding in the back. You've got a concrete pen, concrete wall panel. Just use the shape to do that. And basically, I'm asking you to think about building it. This is just a wall. How you think it's built in a 3D view? I will just put, hopefully, it should be, let me just assume it's, yeah, this is just like in a 3D kind of a view. Go back and use this. Yeah, any thoughts? How would they build a wall like this?
From previous experience,
Yes.
we make the reinforced concrete. It should be connected to the columns and the pad footing or the footing. And when we pour concrete, it will be also connected with the footing.
So what I'm showing here is you're talking about a strip footing that's under. Well,
yes.
Yeah, let's say it's a strip footing, or maybe a concrete floor, or maybe a pile cap, or maybe another wall. So regardless, whatever the base is, right? So I'm just here drafting the blue. It is just a footing system that will carry the wall we are discussing here. But again, my question is, what are the steps? So let's say the blue, it is a strip footing, and definitely when you're going to be pouring your strip footing, you're going to leave some starter bars sticking out from your strip footing like this. And I think that was what you were talking about. So imagine the wall is not there. What you're going to be doing first?
Formwork.
Formwork, excellent. You have to go and place the formwork. So and I will try to put it here in this magenta color. So yes, we're gonna need to put a formwork, which requires, my point is, which requires typically a lot of work. So it's just a panel. I can show you images from the net for work for reinforced concrete wall. It's usually, here we go. See what you would experience. This is, let me see if we have a bigger picture. That's the classical way of forming up. Usually you put the formwork on one side, yeah, on one side, then the labor are gonna come and put. So you see these bars, these were the starter bars sticking out from below, whether it's a slab or another wall or a strip footing, which was that blue color. Then that purple sheet, it is one side of the formwork, and imagine that they're gonna need a lot of propping work. Usually they are very sensitive because when you build a wall, you have to build it straight up. You have to be very careful with building it. And there are very kind of robust measurements to do. Then you're going to be propping it like this every 600, 400. It depends on the thickness of the wall. So what I'm trying to say, it's a lot of work. Usually, it's not something that can really happen with a simple process or fast erection process. Now that's one thing. Then after you place the reinforcement. So before we pour the wall, we're gonna place the reinforcement, which you would have vertical and horizontal like that. You will be placing the other face of the formwork as well, like what I'm just showing you here, right? And then you need a prop. Not only that, after you place all the propping lines on that purple that I'm putting to you on both sides, you have to actually use some special bolts. I will put them in green. Those bolts, they actually go through the wall again, whatever the engineer wants, every half a meter or 600 like this, because they're gonna make sure the wall won't burst out when you're gonna pump in the concrete. When you pump it in, there's going to be a lot of pressure that will be pushing inside out. If you don't have that strong, which again you will see in this image, you see here, you can see those little, I tried to zoom there, but I'm not sure if I lost. Here we go. I'm sure if that's something else. So you see these little things, they are kind of bolts go through. So one of the issues you see with those walls is you see always holes. Around my area, there are some old reinforced concrete walls, and there are holes inside them. And basically the reason for those holes, if they're not patched, because you need them for construction. So coming back to this point, yeah, my point is there's a lot of formwork that we need to think about its cost. However, we got this AFS technologies coming in. ASF technologies coming in, and they're going to take away all that formworking process we need to do, the holes, the bolting, and these two types, which one of them we're talking about, the AFS system, as well as the Dinsel, which I will share with you maybe if I see it. They kind of well used in the current construction industry. They simply, I think they were in this picture as well. If I go up here, that's why I wanted to pass it. You see here, but I don't think these are the local ones that this one here. We don't think this is just international webpage, so don't worry about the system. You can see there's kind of a formwork. That formwork got usually the capacity to ensure the straightness of the wall and to ensure it can resist the bursting forces as you pour the concrete. That's what AFS system do, and available and used widely in the local industry, as well as Dinsel. It is used to do the same job. So basically, instead of putting all the formwork on the sides of the wall, you can just put very lightweight plastic-based material. It can be done by 2 people. Then you place the steel inside them and you just pour the concrete. That's it. Everything should work from there. Now, before I go there, sometimes you're gonna struggle to build a concrete wall, and you may, like in the 20 years ago, before they have came up with those systems. Imagine this is a property line here. This orange color here, it is a property line. You've got a property line. That's just a neighbor. You can't do any propping here outside. So usually then you're going to cancel the idea of having concrete wall. You have to go and use block wall, reinforced block wall, which is more cost and very slow and etc. etc. So coming back to this technology, it is going to take away all the propping needs. It's fast to erect. You can do it whether you are at boundary or away from boundary. You don't need to have those holes. And one of the key advantages, this one, it's gonna give you straight away the architectural finish you want. You don't need to render it. It's gonna give you, it's like ready to paint. These panels, which I think, here we go. So that's the product I'm talking about here. The AFS, the architectural framing systems, right? They got this finish here. It's ready to paint. You're going to save all the time in plastering. You're going to save all the time in patching the walls and doing all the lockups. It's really ready to paint. Now, as you can see, the ASF system is typically built in the factory, and that's how they are ordered. And they are made out of this element here. It is a metal-based material, so it's kind of a lattice structure, which takes away that bursting force I was talking to you about. It's lightweight steel. It's cold formed. It's not the heavy-duty steel. You know, last week in the Wednesday during the workshop in Bendigo, when people were asking me those composite columns, they are built from heavy-duty steel, thick steel, but this one is lightweight, the cold formed. You know, the steel they use to do the lintels and girts, this is lightweight, cold formed steel. Same steel is used here, so it's not heavy-duty steel. It's very light. It's even light to carry by 2 people and place it in position. Yeah, you're going to have those every, say, 400 or whatever. Then you can put your reinforcement for the wall within the holes or the openings, and then you have your vertical reinforcement as per the engineering drawings. And then when you position them straight up, you put the reinforcement. You just come and pour your concrete, vibrate the concrete, and done. Wait for it for a few days or whenever you reach a few weeks, whenever you reach a concrete strength, your wall is ready. Go build the other floor. So the key thing is you saved the propping needs. You're going to have a ready to service finishes. Now, as I said, this is all coming from the ASF manufacturer. The AFS manufacturers, and they come in with different thicknesses. They can be 1200 millimeters thick, 120 millimeter thick, 150 millimeter thick, a bit bigger, or up to 200. Now, well, the sizes are there. It depends on the capacity. The engineer will be designing the quantity of steel required, and basically it have to be placed within all those thicknesses. The benefits, again, when you can be summarized in the sheet: speed, structural capacity. Yes, it gives us the capacity they want. Performance and quality in terms of the final product, ready to paint, and efficiency overall construction processes. At the height, it can 200 height can go up to 4.2 meters in height, so it's quite decent. Now, one of the key things which again can be claimed, and with the engineering reports we read from these walls, you know, if you design an in situ concrete wall, you have to spend high quality of steel to control cracks, right? To control cracks. However, and as per the standards, we need to control cracks to very small limit, where we need to keep the crack with up to 0.3 millimeter. 0.3 millimeter is very small, but to make sure those walls, because mostly those walls are externals, to make sure to stop all water getting through and humidity and all that, the cracks have to be well controlled. So what I'm trying to say is there's going to be a lot of steel required for such in situ concrete walls. However, when you have these walls, by the standards, we don't need to worry about having excessive crack control reinforcement, because it's got its permanent coverage. We're not worried to have those cracks to be controlled. Even if there are cracks that won't compromise capacity, we're not worried about durability, because we got them fully enclosed by the plaster-based product. Okay. So some detailing. You can see those vertical elements. They can come in different shapes. Those vertical elements, they come like small channels. Yeah. They can come up with small channels, and they are the openings here within this wall where you can place your vertical. This is a plan view, in case you did not. This is a plan view of the wall. We're looking at the wall from the top. You have the channels placed like that, and they got the voids where it's going to allow us to place the horizontal bars. And here you're going to got the vertical bars as required by the engineer. Maybe he need N16s, maybe N12s. Maybe they're going to need 2 bars. Yeah, between the channels. And as you can see, they do have some capacity tables for us to use. So these kind of details there for the engineers to use and calculate the quantity, the capacity for these walls, and calculate the quantity of additional steel required to put between the channels. A vertical elevation for those channels is as shown, which is that's just the dimension is going to be useful for the contractors to place their bars and make sure whatever the engineer wanted can be placed within these holes or these openings within your channels. So this is just an elevation for one channel. As we said, it starts, this is for 120 thick wall. The wall can go bigger, up to 200 thick. So these dimensions will be useful to allow. Sometimes the engineers, now I will come to another key use of those walls. They still can be used as retaining walls. And some of those cementitious-based finishes, they can guarantee for you the waterproofing requirements. Now, if you remember, and what you're going to be showing me in assignment 2, and maybe Wednesday and this week, you're going to be showing how the precast walls going to be used. You know, for the basement, when I ask you in question 6, one of the things you're going to document is you need to put the waterproofing membrane between the wall and the soil. Now, these products, they kind of guarantee for you that it is actually waterproofing. They're going to give you that waterproofing, that you don't need to put any paint or sheeting if that wall was used as a retaining wall in the basement. So yes, it can be used. Yeah, that's all usable. So imagine if we have a retaining wall, definitely you need a quite thick wall, which can be up to 200 thick. And the reinforcement, by the way, maybe you need them in both sides, not only one side or in the middle. So if you got a wall carrying lightweight load, still load, but not a lot, you may end up using 150 thick or even less, maybe 120 thick wall, and your reinforcement can be only in the middle. Right? But if you go to heavy duty walls, your reinforcement may be placed on both sides, the soil side and the basement side. Yeah, so that's where when you're going to work in this area, you have to carefully read the engineering drawings. They may need the reinforcement on both sides of the wall, especially for 200 thick walls. Right? Yes, there are some arrangements, to consider when the contractors support. Definitely when you're going to have contractors to construct such walls, they're going to be having such experience. You don't need to use people who never used it before. And really the challenges from friends, construction engineers I know, is they sometimes come up with, they say, I want to use this type, but they don't bring the correct contractors. Like they bring contractors who have experience in building normal in situ concrete walls. Or they may bring people who usually got experience in pouring columns or slabs. No, there are some different techniques have to be followed, which people can always read from the supplier. So all these notes really coming from the suppliers, which is the AFS manufacturer. They give recommendations in terms of pouring the concrete. For example, there is a maximum height when you concrete pour limits to 150 height lift, so you cannot pour like imagine you just started pouring here, you cannot throw the concrete from this height. You have to actually impose the pipe into the wall more, so you have to go about 1.5 meter high. You want to have that self-compaction. Why are we doing all that? We need to make sure the concrete is self-compacted. The reason behind all that, you don't have a lot of gaps here. Remember, here we're going to still have reinforcement on the sides and reinforcement in the vertical, so the gaps will be small. You need to make sure when you pour the concrete, you don't throw it. If it's still empty without any concrete, you don't pour the concrete from this height. You have to submerge your pipe all the way down to halfway, maybe. If it's 3 meters height, halfway, and that will ensure you are dropping the concrete at 1.5 meters high, right? So there are kind of recommendation provided by ASF to AFS, sorry, to make sure the compaction arrangement will be done appropriately, right? So there's also admixtures recommendations, again, to make sure the aggregates will be possible to, will be small enough and will be possible to get all the concrete within the small gaps and spacings between the channels and the bars or between the bars themselves. Right, slump test for the concrete mix to be within this range is quite high. Yeah, 150. So the concrete is quite loose, and usually, you know, when you know that the use of fly ash. Fly ash is kind of within the mix of concrete just to have a better rating of a green concrete. So you can fly ash is a recycled product that people nowadays can use in the mix of concrete, which will end up resulting in a high workable concrete in terms of its slump. Now, usually, now when we add fly ash, it will reduce the capacity, but the capacity, as you can see here, it can range between 25 to 50. So, as I said, we're not heavily worried about crack control. We need it to be within the adequate limits that will give you the strength. But in terms of appearance, this is already achieved by having this finish, by having the architectural finish already concealing the wall permanently. So it's a permanent formwork, right? That will look after the architectural serviceability of the wall. If it was a normal wall, and in case if it is a retaining wall, it will give you that waterproofing requirement. Okay, and there is, yeah, just kind of some ideas about the size of the piping tube, which is to ensure it can work for you. Again, you don't need to have tools which cannot fit the available size. And just to let you know, like what I was talking to you about, the height of pouring the concrete, this is also the same thing applies for a block wall. I remember inspecting one of the block walls. I've actually got the picture somewhere. There's a 140 thick block wall, And after they done all the construction process, next day there was a test done, and they found, so if that was, so this is your elevation for the wall, right? A block wall, that was the elevation. And they found a big area, it's got no concrete. It's got no concrete. Like you can see even at the end of the day after they pour the, so what they do, they pour the concrete from the top, and it was only 140 thick block wall, so it's a bit small, so it needed really small pipes, and it needed to be poured from lower level, but we think that this was not all done, and there was a big part here without any concrete. And by the end of pouring it, when we've seen some pictures, you can see this whole area here, the one I'm shading with orange, you can feel it's like wet, because when you pour the concrete, not for those floors, for a block wall, you can see that it was wet. It is wet within the first, like after 2 hours or 1 hour when you pour the concrete, you can see it's kind of wet from the moisture. But there's a big area here. I'm talking here about maybe 7 meters long wall. It's quite long. You will see there's a lot of area in the bottom which is dry. There was no wall, and then they knocked this part. They found there is no concrete. Then they decided to knock the whole wall down. It was a really long wall. It was all knocked down and have to be redone from the start. So it is very costly to just not have the right people doing particular, pouring concrete is not just skipping something and throwing it. You have to make sure it's well vibrated and well compacted as well. So that's exactly the same point. What I'm trying to say, whatever applies here, it applies on any other types of walls. I know in this subject we didn't had a subject talking about block walls. If you want to see, maybe I can show you. Locally, it is used, but mostly in residential constructions. Block wall, let's say reinforced. Let's say 140 thick. Yeah, this is kind of one unit of a block wall, but I just want to show you how it's built. Here we go, something like this. You see them around. This goes from the smallest thickness. It can be 140, like you see here, but it goes up to 290. Can be as wide as 290. One of the issues with these block walls, you can see here, yeah, like they need to fill all those voids. And usually the mistakes or the challenges is you need to make sure it's poured very well. That's where you need to discharge the concrete at lower heights. Make sure the tubes are actually positioned about mid-height of the wall. And the example I was talking to you about, there are cases where after they pour the concrete, if people haven't done the correct compaction and didn't have the correct workable slump concrete, you may end up having a lot of gaps within the wall, which can be straight away rejected. And you just need to demolish again. Okay. Yeah, but I know we did not really have a topic talking about this type of walls, but it just it's mostly used for residential constructions. All right. Reinforcement. So as I think this was the note I was talking to you about. There are reinforcement, which is mostly to do for strength. Yeah, so the reinforcement typically it is specified by the engineers. We're going to be sizing the quantity of reinforcement, vertical and horizontal. As I said, there are some discussions. This slide is talking about the minimum reinforcement for crack control. But to some stage, the wall itself, right? It's got its own capacity to take it, especially talking about the other brand name, Denso. The Denso product as well. It's a different wall system, DINCL, Denso. So maybe we got a few minutes to go. Denso wall. Yeah, here we go. just images. Now, Denso is kind of, if you see its formwork, it's even lighter. The formwork, it's even lighter. You know those channels here? It's actually a polymer based, but it's high duty. So it's still doing the job. And as I said to you, it's well used as well. And it can give you all that waterproofing for retaining walls. I can see, I think here it's a retaining wall. And it's not anymore the ribs inside them. I'm not sure if there is a better, closer picture. There is no steel channels. It is mostly just a pulley-based product. The entire unit is pulley-based product. There is even those horizontal elements, they are not steel. So it's very lightweight in terms of construction and very fast to build. It's like a cardboard. You just go and place them, and you put your steel. As I said, you see here we got 2 holes. We use this for retaining walls because we can place the bars in the right position. We can put them on both sides, right? And you can see the level of reinforcement and placing the reinforcement. That's at the corner what we have to do there as well. So yeah, that's just a pouring process. So this is, as I said, 2 famous brand names, Tensor Wall and you can see how lightweight it is. That just one unit. They place it next to each other, and then it's going to be ready to. There are few propping lines that may be required, but few. You can see the level of propping, and you need it only from one side, by the way, only from one side, not both sides, if deemed to be required. Now, what I was talking to you about this, usually there are research done by Denso, which kind of saying you can omit all the crack needs. I don't want to take you through a lot of detailed engineering thoughts here, but Denso, for example, it helps engineers to eliminate all crack control reinforcement to some stage. AFS, they still ask for some limited quantity of steel, but things may change, depends on how they want to take things. But at the end of the day, this is all documented by the structural engineer, who will give you engineering drawings like what I shared with you for the other topics. So they're going to be engineering drawings to tell you how the quantity of steel, and it just need to be built as per. In terms of cost, you will save steel, you will save formwork time, you will save the propping time as well significantly. Yeah, some pictures similar to the ones I showed you. There are shop drawings which really build shop drawings. There's something similar to the shop drawings for the precast panels, which I talked to you carefully about. So same process. You're gonna have engineering drawings which specifies the main steel components and framing components for the wall. Then you can, if it's a large project built with a lot of such walls, you can request shop drawings, which can give you detailed sizing. If you got few walls, you can work this out with the engineer straight away. Right, this just shows you a picture about this system, the AFS system, how it's used widely. This is, you can easily see it's an apartment construction. And or you can actually watch some videos, yeah, to see all those. This is by the supplier who really provided for and I think some of them, they keep updating them. Maybe, as I said to you, a few years ago, AFS were asking for a crack control reinforcement, but I think nowadays they have different arrangements where they don't want additional reinforcement. So construction process and all those detailing, coring, core filling, they allow for making holes within the walls. All is actually it is kind of provided in the websites from AFS, which you can watch, but don't expect in the exam we're going to ask you to answer some information provided within those videos. It's good to keep them in your library in case you want to discuss an option or talk about, like nowadays, even homeowners who like to have some concrete within their properties, they would go with these options. So it's good to know about it. But the key advantages really I talked to you about is the fast direction. It's what we discussed earlier, and saving all that propping costs, propping time. You can build that boundary, it can give you the waterproofing, it can help you to control the cracks or the wall. So these are our 3 other advanced systems I wanted to share with you before the end of the topics. So by now I'm done, and I think the time is done as well. So the topics are done, and try to come into the workshop as many as you guys, to give you as much support and feedback I can for your second assignment. And we can talk about general things if the time allows. Next week will be a general revision, careful revision about all the topics, and some hints and some guidelines for preparing to the final exam. It's 10:01 and we should be done. Any questions?